So there are four features you want to look at to read an NMR spectrum, and those are, first, the number of signals that you have. That tells you about the number of different electronic environments for the hydrogens. The second is the location of the signals, and that depends on the types of bonds and atoms nearby. So that's like the number of electronegative atoms that will steal electrons away and create a different electronic environment and shift the signal, or magnetic anisotropy. The third one is the area underneath each signal, and that has to do with how many hydrogens there are in each electronic environment. Each signal represents an electronic environment, and the area underneath each signal, so for example, between these two signals, the one on the left has a very small area underneath it. The one on the right has a much bigger area underneath it. So the area under each signal tells you how many hydrogens that are in each electronic environment. So for example, if you had these two signals, this one on the left is smaller, it has a smaller area underneath it, and so that means there are fewer hydrogens in that environment than there would be in the environment represented by the other peak. And the fourth thing we'll get to in another video. For this one, we want to practice this area. And so what we do is they'll give you a spectrum, something like this, and they give you a molecular formula, and they ask you to determine the number of protons giving rise to each signal. So we have four signals here, 1, 2, 3, and 4, and each of those are representing a different electronic environment in this molecule. And we want to know how many hydrogens are in each of those environments. And so you take the area. Now the mathematical operation you use to take the area underneath a curve is called an integral. Now we're not going to take any integrals in this class, but a computer will do it for us, but that's where this term integration value is coming from. It's referring back to the integrals that you're taking, that mathematical operation, to find the area underneath a curve. Okay, so that's what these red numbers are. They're the relative amounts of space underneath each of those peaks. They're telling you how much area is in those shadows, how big those shadows are. And that's related to the number of hydrogens in each of those environments. Now these are not really useful numbers as they are. They're weird, sort of non-intuitive numbers. So we want to turn them into the number of hydrogens. And the first step for doing that is to turn them into more intuitive numbers, simpler numbers. So you can do that. You can get the ratio between these, the simplest whole number ratio, by dividing each of these red numbers by the smallest one. The smallest one is 33.2, so we'll divide each of these numbers by 33.2. All right, now with these, for me, you will either want to round to a whole number or to a 0.5, whichever one's closer. So here, this would be 1. This would be rounded to 1.5. That's what that's closest to. This is 1, and this would be rounded to 1.5. That's what that's closest to. Now remember, these are the number of hydrogens that are in these electronic environments. And you can't have half of a hydrogen. So these numbers are not the number of hydrogens under these peaks. They're just the ratio. To get them to be whole numbers so that they make sense, I mean, they're numbers of hydrogens, they have to be whole numbers, we're going to multiply all of these by 2. That'll turn the 0.5s into whole numbers. So that gives us 2, right, if you distribute that. If you distribute this 3 to the next term 2, and to the last term 3. So those, again, are ratios. These are possible numbers for the number of hydrogens in each of these peaks. That peak, for every 2 hydrogens in that peak, there are 3 hydrogens in this peak. Now, at this point, these are just relative numbers. For every 2 in the first peak, you have 3 in the next peak, but that doesn't mean that you have those exact numbers in the molecule. To figure out whether those are just the relative numbers or the exact numbers, add them up. If you add these all up, you'll see that it gives you 10. So these would give you a total of 10 hydrogens. And compare that with the number of hydrogens in the molecule. The molecular formula gives you 10 hydrogens. And remember, you would get this, they're giving you this molecular formula in the problem, but in the laboratory, you would figure that out using mass spectrometry. So they're giving you these 10 hydrogens in the problem. That's how many you get when you have these ratios. That means that these are the correct ratios. And so in this first peak, there really are, that is representing an electronic environment that has only 2 hydrogens in it. This next peak is representing an electronic environment that has 3 hydrogens in it. That's representing an electronic environment that has 2 hydrogens in it. And this last one is representing an electronic environment that has 3 hydrogens in it. And so that's the number of protons giving rise to each of these signals. 2 protons, 3 protons, 2 protons, and 3 protons. All right, let's follow that same procedure with 1612. So we have 1, 2, 3. You know they're different because they have different numbers pointing at them. 4 different peaks. So we have 4 different electronic environments for whatever this molecule is. And you'll notice that they give us the molecular formula here. That's something that we could find in a laboratory using mass spectrometry. Okay, they give us these weird, non-intuitive numbers. The computer spits those out. So to make those more intuitive, we divide them all by the smallest number that they give us, and that's 17.1. So 17.1 divided by 17.1 is 1. So this will just be 1. 87.1 divided by 17.1 would give you around 5. So this gives you around 5. 18.7 divided by 17.1 gives you essentially 1. Remember, you're rounding to either the closest whole number or to 0.5 if that's closer. And then 51.1 divided by 17.1, that's about 3. All right, so these are the relative amounts of hydrogens in these different electronic environments. For every 1 hydrogen in this electronic environment, there would be 5 in this one. And for every 5 in that one, there would be 1 in that one. So those are the relative numbers. But what we want to know is, are they the absolute numbers? Is that the actual number of hydrogens in that electronic environment for this molecule? And to figure that out, you want to add them all up. See what total this would give you. And so if you add all these up, you'll see it gives you 10. Compare that with the number of hydrogens in the molecule. There are 10. And because those numbers are the same, that means these must be the numbers of hydrogens in each of these peaks. This first peak really does have 1 hydrogen in it. This next one does have 5 hydrogens in it. The next one does have 1 hydrogen in it. That electronic environment does have 3 hydrogens in it. And so it says determine the number of protons giving rise to each signal. 1 proton is giving rise to that first signal. 5 protons are giving rise to the second one. 1 proton is giving rise to the third one. And 3 protons are giving rise to that rightmost one. All right, we can take that same procedure and apply it to 1613. They give us a molecular formula, and they give us the areas underneath these 3 different peaks. Now, each one of these peaks represents a different electronic environment in whatever molecule this is. So those numbers they give us, the integration values, the areas under those peaks, are very non-intuitive. It's just a number that the computer spit out when it was comparing them all. So to make them more intuitive, we divide by the smallest one. That's 18.92. And that gives you 1, 1, and 1. if you round them so that you're either getting to the closest whole number or to the closest 0.5, then you'll see that they all are closest to 1. Okay, so those are the relative values. What that means is that for every 1 hydrogen you have in this peak, you have 1 hydrogen in the next one and 1 hydrogen in the next one. Those are the relative values, but are they the actual number of hydrogens, the absolute values for this molecule? To figure that out, you add all of these up. So that gives you a total of 3 hydrogens. And compare that number with the number of hydrogens in the molecule. So the number of hydrogens in the molecule is not 3, it's 6. And so what would we have to multiply 3 by to give us 6? 2. If you multiply 3 by 2, you get 6. And so that means that each of these environments you'd have to multiply by 2 so that there would be 2 hydrogens represented in this first peak, 2 more hydrogens represented in this second peak, and 2 more hydrogens represented in that third electronic environment. And that gives you a total of 6. So it's asking you to determine the number of protons giving rise to each signal. Well, this signal is being created by 2 protons, this one being created by 2 protons, this one being created by 2 protons. Remember, hydrogen only has 1 proton in its nucleus, so hydrogen and a proton, those terms are often used synonymously. All right, so that's sort of how you can use those integration values to figure out the number of hydrogens in each of the electronic environments represented by the different peaks.